In the previous videos on communication, we have studied the need of modulation in communication of an audio signal and the characteristics of amplitude modulated wave. Now presently we will study generation of amplitude modulated wave. In the previous sections, we already have discussed that the amplitude modulated wave can be divided into different categories. The first is double sideband full carrier wave. The next is double sideband suppressed carrier wave, and after that single sideband and vestigial sideband amplitude modulated wave. The basic AM wave is double sideband full carrier wave, or in abbreviated form it is designated as DSB-FC. First we will consider the generation of DSB-FC, that is the amplitude modulated wave in which full carrier along with two sidebands is present. For generation of DSB-FC, the device is a square law modulator. In this square law modulator, we make use of an electronic device whose characteristics depend upon a square law. Or in other words, we can say that we use an electronic device in which the current is directly proportional to the square of applied voltage. The example of nonlinear devices are diode, transistor, iron core inductor, etc. If we study the current voltage characteristics of these devices, then we will find that the curve is highly nonlinear. As we know the characteristics of PN junction diode, and if we analyze these characteristics, then we come to know that in the lower applied voltage, the variation of current in the circuit varies in a non-linear manner with the applied voltage, and for the higher voltages it is somewhat appears as linear variation, but when the applied voltage is low, then the variation is highly non-linear. Therefore, we can use PN junction diode as the square law modulator. So in the figure, the circuit of a square law modulator is shown. We have used the PN junction diode, and in the circuit we are applying the RF input voltage, which is the carrier signal, and there is audio input, which is modulating signal. LC is the tank circuit, which is used to select a single frequency out of many frequencies that are present in the circuit. And across the tank circuit or the LC circuit, there is a resistor, and across this resistor we get output voltage. Now we know that the diode is a non-linear device, therefore the current flowing in the circuit will be I is equal to A into V plus B into V square, where V is the applied voltage and I is the current in the circuit. As we are using two different types of voltage in this circuit, the first is the modulating signal, which is represented by the equation Vm is equal to Vm cos omega mt, and the other is the RF input or the carrier signal, which is represented by Vc is equal to Vc cos omega ct, and the sum of these two voltages will come out to be V, which is used in the circuit. I is equal to A into V plus B into V square. So this is the equation of current flowing in this circuit of a square law modulator. As in the previous slide, I have described that the total voltage across the diode would be Vm plus Vc. So it is Vm cos omega mt plus Vc cos omega ct. Therefore, the current in the circuit will be A Vm cos omega mt plus Vc cos omega ct, plus the second term is B into Vm cos omega mt plus Vc cos omega ct whole square. Now we have expanded different terms in the equation, and the final equation can be seen in the slide. This is the equation in its expanded form. If we analyze different terms in the circuit, then we can make out that the first term A into Vm cos omega mt is the modulating term, modulating signal term, or in this term omega m is the modulating frequency. In the second term A Vc cos omega ct, the frequency which is present is carrier frequency, that is omega c. The terms BVm square by 2 and BVC square by 2, these two terms are the DC components, because the variable terms which depend on the frequency are not present there. Therefore, these two terms are constant terms. Remaining terms, that is BVm Vc cos omega m plus omega ct plus cos omega m minus omega ct, these are the side bands. It is the first one is the upper side band and the second one is the lower side band. In the second line of this expansion, some trigonometrical transformations or trigonometrical substitutions and equations have been used, and if the candidate or the student is will go through these calculations, then the first equation can be easily converted into the second equation, and by using this kind of trigonometrical transformation we can get the second equation easily. Now in the circuit which is shown in the previous slide, we have used an LC circuit or the tank circuit at the output, and the resonant frequency of that tank circuit is fixed at the carrier frequency omega c. It means that if the resonant frequency is omega c, hence for this frequency omega c, the current in the tank circuit will be maximum, and for other frequencies the current in the circuit will be minimum and fall off to 0. Hence we can say that for the frequency omega c, the current will be the largest, and for a modulating frequency omega mt, the current will be minimum or nearly 0. Similarly, the constant terms, that is BVm square by 2 and BVC square by 2, these are the DC components. They will also be suppressed at the output because the resonant frequency is fixed at omega c. Now These two terms, modulating frequency and the DC component, these two terms have been discarded at the output circuit. Now what happens to the term omega c? It will be present at the output because the resonant frequency is fixed at omega c. Now the question arises, what happens to the sidebands? Since we have fixed the resonant frequency at omega c, and omega m is much smaller than omega c. Hence, we can say that omega c plus omega m and omega c minus omega m, these two terms or these two values are not much different from the carrier frequency omega c, because omega c is in the range of megahertz and omega m is in the range of maximum value of omega m is 20 kilohertz. Therefore, omega c minus omega m and omega c plus omega m are very close to the resonant frequency omega c. So we can conclude that along with the carrier frequency omega c, the lower sideband omega c minus omega m and upper sideband omega c plus omega m are also present in the output voltage. Hence, the three terms will be present in the output signal, and those terms will be the carrier term, that is A into Vc cos omega Ct, because this is the resonant frequency is equal to the carrier frequency, and the lower sideband omega c minus omega m term and the upper sideband omega c plus omega m. And this was the aim of this circuit, to get at the output the signal in which carrier component and the two sidebands, lower sideband and the upper sideband, are present. That is, we are getting double sideband and full carrier wave at the output of a square law modulator. So with the help of a square law modulator, we can generate double sideband full carrier wave. Now comes balanced modulator, and this circuit is used for generating DSB-SC, that is double sideband and suppressed carrier. Or in other words, we can say that the aim of this circuit is to produce a wave in which the upper sideband and the lower sideband are present, but the carrier component of the modulated wave has been suppressed. The circuit of the balanced modulator is shown in this figure. We are using two transformers. The transformer at the input circuit, this is center tapped transformer, and at the output circuit also we are using a transformer which is also center tapped. In fact, we are using one more transformer which is shown in this in the figure at the center, and across this transformer we are applying the carrier wave or the radio frequency wave, and the modulating signal or the audio signal is applied across the transformer which is connected directly at the input. In addition to that, two diodes D1 and D2 are used, and the transformer at the output circuit is providing a tank circuit, the secondary of the transformer, and a capacitor which is connected across the secondary. They both are forming a tank circuit which will be used as the selective circuit. Or we can say that as in the previous case, across the output we had connected a tank circuit which was used to select a particular frequency. In the same manner, in this case also, the secondary of the transformer at the output along with the capacitor will be used as the tank circuit, which will select a particular frequency for the output voltage. Now if we analyze the current flowing through the circuit, then the first term is Vm cos omega mt. This is the modulating signal. Omega c minus omega mt, this term is lower sideband, and omega c plus omega mt, this is the upper sideband. Now the transformer or the tank circuit at the output circuit is tuned at the carrier frequency as in the previous case. So when the circuit is tuned at the carrier frequency omega c, then omega m will be, naturally it will be rejected or it will be discarded. So the modulating signal will be discarded. The pure carrier signal is not present in the expression for the current. Though the circuit, the tuned circuit is tuned at the carrier frequency omega c, but the carrier component is not present. Therefore, we can say that the carrier has been cancelled out, or the carrier component will not be present in the output voltage. The two voltages or the two components that are present in the current are lower sideband omega c minus omega mt and the upper sideband omega c plus omega mt. Since the resonant frequency of the tuned circuit is omega c, and omega c minus omega m and omega c plus omega m do not differ too much from the carrier frequency omega c, which is also the resonant frequency. So we can say that through the resonant circuit or through the tank circuit, these two frequencies will be passed, and at the output resistor or at the output we will get the two sidebands, lower sideband and the upper sideband. And the reason for this case why the sidebands are passed through the tank circuit, it was discussed earlier also. Since the carrier frequency omega c is very high, it lies in the radio frequency range, and the modulating frequency omega m is comparatively much lower. The highest value is only 20 kilohertz. So the value of omega c minus omega m and omega c plus omega m do not differ much from the value of omega c, which is the resonant frequency. Hence the result is that with the help of the balanced modulator, we can get at the output a wave in which the two sidebands are present, but the carrier component is absent. Therefore, this method is being used for the generation of double sideband and suppressed carrier wave, that is DSB-SC. Now the next circuit which we are going to discuss is a ring modulator, which is also called chopper modulator, and this circuit is used for the generation of DSB-SC, that is double sideband and suppressed carrier. As we can see in this diagram, two transformers which are indicated as T1 and T2, they are used as the input transformer and the output transformer, and both of them are center tapped transformers. Across the primary of the transformer T1, the modulating signal or the audio frequency is being applied, and across the center tapping of both the transformers, the radio frequency signal or the carrier wave is being applied. As we can see from this diagram, the radio frequency carrier wave is taken in the form of a square wave. So the carrier wave is a high frequency radio frequency wave in the square wave shape. And 4 diodes are being used, D1, D2, D3 and D4, since they are used in the form of a ring. The circuit, if we analyze it or if we see it minutely, then the 4 diodes are forming a ring, therefore it is known as a ring modulator. And across the secondary of the output transformer T2, capacitor is connected, and along with that secondary of the output transformer, it is forming an LC circuit, or the circuit which can be uh, used to reject certain frequencies and select other frequencies depending on the resonant frequency of this LC circuit. Now, the main important point in in the discussion of ring modulator is that the amplitude of this RF carrier wave is taken to be much higher than the amplitude of the modulating signal. About the frequency, we know that the frequency of carrier wave is naturally much higher than the frequency of the modulating signal, but we have to uh, ensure that the amplitude of the RF carrier signal should be much larger than the amplitude of the modulating signal. This kind of arrangement is to ensure that it is the carrier wave which is the deciding factor to decide what is the biasing voltage, whether the diodes should be in the forward bias or in the reverse bias. The carrier wave should decide whether which of the diodes should be in the forward bias mode and which diodes have to be in the reverse bias mode or in the non operative mode. Why this kind of arrangement is made, it will be clear from the next slides when we will discuss the operation of ring modulator in detail. So one thing we have to put or we have to keep in our mind that whether the diode will be in the forward bias or in the reverse bias, it will depend upon the radio frequency carrier wave, not on the polarity of the modulating signal. This is very important point to be noted with ring modulator. To understand the full operation of ring modulator or chopper modulator, let us divide the working into two parts. The first is without applying the modulating signal, and the second is the operation with the modulating signal. In the normal operation of the chopper modulator, we apply the audio signal or the modulating signal across the primary of the transformer T1 and the RF carrier wave across the center tapping of the transformer T1 and the transformer T2. This arrangement is for the normal operation of ring modulator. But to understand the full operation in easy terms, let us first consider what happens when we are applying only the carrier wave across the two center tappings of the transformer T1 and T2. That is, we are not applying the modulating signal across the primary of the transformer T1. This is only for understanding the working of the modulator. When only the carrier wave is being applied, and we will consider the positive half of the carrier wave. Suppose the positive half of the carrier wave is being applied, and for this half of the wave, Suppose the left part or the terminal which is connected to the transformer T1 is positive, and the second terminal which is connected to the center tap of transformer T2 is negative. This is the case when we are considering the positive half of the carrier wave. When this point is positive, it means that it is evident from the figure that the P part or the P terminal of diode D1 is connected to positive, and the P side of the diode D2 is also connected to the positive potential, and the other end of the uh, points across which the RF carrier wave is connected is negative. So the negative potential is connected to the center tapping of the transformer T2. Therefore, the N side of diode D1 as well as of diode D2 are placed at the negative potential. Therefore, for the positive half cycle of RF carrier wave, both the diodes D1 and D2 are forward biased. When the diodes are forward biased, then it means that the current is flowing through the two diodes. The direction of the current is represented by the direction of arrow present in the symbol of the diode. So, the direction of current flowing through the diode D1 is shown by the arrows. This is the direction of current, or in other words, we can say that the current through the diode D1 is flowing in the clockwise direction. If we consider the diode D2, then the arrows in the lower part of the circuit are showing the direction of current through the diode D2, and the current is flowing in the anti-clockwise direction through the primary of the transformer T2. If we concentrate upon the currents flowing in the primary of the transformer T2, and the back current coming from the diode D1 is flowing in the downward direction, and the current coming from the diode D2 is flowing in the upward direction. Hence, the magnetic fields which are generated by the flow of these two currents, they will be in the opposite direction. So, the magnetic fields will cancel out each other, and the output circuit or in the secondary of the transformer T2, the net magnetic field or uh, current will be zero. Or we can say in other words that the output voltage will be zero. This is the case when we are applying only the carrier wave and we are considering the positive half cycle of the carrier wave. So in this case we can conclude that if we are considering the positive half of the carrier wave with zero modulating signal, then the output voltage will be zero. Now we come to the second part of the operation, that is we are not applying the modulating signal. We are dealing with the application of only the carrier wave. In the previous slide, we had considered the operation with the positive half of the carrier wave. Now we will consider the case with the negative half cycle of the carrier wave. So in the present case, since we are dealing with the negative half cycle, so the part of the carrier wave or the terminal of the carrier wave which is connected to the secondary of a transformer T1 will be negative, and the terminal which is connected to the center tapping of transformer T2 will be positive, because in the previous case the polarities were opposite in the previous slide. So when the terminal in the secondary of transformer T1 is negative. So we can say that the diode D1 and the diode D2 will be reverse biased. We can see it from the circuit in the previous slide, that if this end is negative, then the diode D1, which is connected between A and B, will be reverse biased, as well as the diode D2, which is connected between C and D, will also be reverse biased. But if we concentrate upon the diode D3 and D2, then we can see from this figure or from the circuit diagram that this end is connected to the negative potential. So when this point is negative, and we can say that this point of at negative potential is connected through the point C to the N side of diode D3. This is the diode D3. So N part is connected to the negative terminal like this. Similarly, this point is positive. So when the terminal which is connected to the transformer T2 is positive, and we can say that this terminal is connected to the positive side of the diode D4. Therefore, P of diode D4 is positive and N of diode D3 is negative. So both the diodes D3 and D4 are in the conducting mode when we are applying the negative cycle of the carrier wave. So if the two diodes are in the conducting mode, and then they will current will flow through both the diodes. If you consider the diode D3, then the current flowing through this diode, it is shown by the direction of arrows. The current is starting from the diode D3. It is moving like this. It is moved like this through the secondary of the transformer T1. It moved like this through the 2 points between which the RF carrier is applied. It will move in the upward direction, and when it comes to the direction of when it comes to the primary of transformer T2, then it will go upwards. Then again it will go to diode D3. From diode D3, again it will follow the same direction as previously, upwards, then through the RF carrier wave like this. Then it will go to the again to the primary of transformer T2, then in the upward direction again through the diode D3. Hence we can say that the current which was started from the diode D3, it moves in the upward direction in the primary of transformer T2. Now what happens with the diode D4? Since diode D4 is also forward biased, so the current will start in the direction of the arrow. The current will flow in this direction, in the direction of arrow. It will move like this, then it will go through the secondary of the transformer T1. It will pass through the two terminals between which the RF carrier is being applied. Then it will go upwards. It will move to the secondary of the primary of the transformer T2. From the primary, it will come down and go to the diode D4. It will pass through diode D4, and again it will follow the same path as discussed previously. So we can say that if we concentrate on the direction of current through the primary of the transformer T2, and we can say that the current which was originated from the diode D3, it was moving in the upward direction, and the current which was which was originated from the diode D4, it is moving in the downward direction in the primary of the transformer T2. Therefore, we can say that both the currents are flowing in the primary of the transformer in the opposite direction, and they will ultimately cancel out the magnetic fields which are produced by the flow of these two currents. Hence the magnetic fields will be cancelled out, and the voltage which was supposed to be produced across the output circuit due to the flow of current in the primary circuit will be cancelled out. Hence we can say that, as in the previous case, for the negative half cycle of the carrier wave, again the output voltage will be 0. Or we can say in the conclusion that if the modulating signal is absent, then the carrier wave is not capable of producing any voltage at the output, or the pure carrier component is absent in the output of this kind of modulator. The pure carrier wave is absent, therefore this is the case of suppressed carrier. Since we are going to generate double sideband suppressed carrier, so we are able to generate an output voltage in which the carrier in its pure form will be absent. So in the previous slides, we had seen that if only the carrier wave is applied across the center tappings of the transformer T1 and T2 of the ring modulator, and the modulating signal is absent from the circuit, then the output voltage will be 0. Therefore, we can conclude that in the ring modulator, the pure carrier component is absent in the output, or this is the case of suppressed carrier. But in actual case, along with the carrier wave, the modulating signal will also be present across the input terminals of the modulator. The audio signal we have represented as empty, and it is applied across the input terminals or the primary of the transformer T1, and the carrier signal is a square wave which is being applied between the center tappings of the input transformer T1 and output transformer T2. As we have discussed earlier, the important point in this in the working of a ring modulator is that the amplitude of the carrier wave is much larger than the amplitude of the modulating signal. This arrangement is made in order to ensure that the biasing across the diodes D1, D2, D3 and D4 will be controlled by the amplitude of the carrier signal, or the decision which of the four diodes will be in the forward bias and which of the four diodes will be in the reverse bias will be decided by the amplitude of the carrier signal and not by the modulating signal. The polarity of the carrier signal will decide which of the four diodes will be in the conducting mode and which of the four diodes will be in the non-conducting mode. Now let us concentrate on the positive cycle of the modulating signal. Suppose this is the modulating signal or the audio signal, and we are considering the case when the positive half of the modulating signal is being applied to the circuit. And this is the square wave, or this is the carrier wave. So what happens when the positive pulse of the carrier signal or the carrier wave is being applied? Then what happens in this case? This this end of the of this terminal of this secondary tapping will be positive. That is the terminal which is connected to the secondary of the input transformer will be positive, and the end which is connected to the primary of the output transformer will be negative. So we can say that when this point is positive, therefore the P side of the diode D1 as well as of the diode D2 will be placed at the positive potential, and since the right terminal or this terminal is negative, therefore the N side of the diode D1 and that of diode D2 will be negative. Therefore we can say that for the positive cycle of the square wave, the diodes D1 and D2, they both are in the conducting mode or in the forward bias. When both the diodes D1 and D2 are in the conducting mode, it means that the resistance produced by the diode D1 and the diode D2 will be least. Hence, we can say in other terms that the point A is directly connected to the point C and the point B is directly connected to the point D. Hence, we can say that whatever potential is present at the point A will be directly reflected or will be directly transferred to the point C, or the voltage which is at the point A will be directly transferred to the point C, because the diode D1 is in the conducting mode, therefore point A is directly connected to the point C. Therefore the voltage which is present at the point A will be directly transferred to the point C. Similar is the case for the point B and the point D, because diode D2 is in the conducting mode, therefore whatever potential is present at the point B will be directly transferred to the point D. Or in other words, we can say that for the positive, and this is the case for the positive cycle of the square wave or the carrier wave. When the positive cycle of the carrier wave is being applied, then in that case whatever voltage is present across the secondary of the input transformer, it will be directly transferred to the primary of the output transformer, or whatever signal is for this particular duration. For the duration in which the positive pulse of the square wave is being applied, for that particular case whatever signal is present in the input, that will be reflected at the output. This can be seen from the figure. This is the output voltage of the modulator. This figure is the, or this diagram shows the output voltage across the output terminals of the modulator. In the case for the duration for which the positive square wave was being applied, in that case the voltage which was present in the input will be reflected in the output. For this short duration, the input is reflected at the output. Now let us consider the case when the negative pulse of the square wave or the carrier wave is being applied. As we have seen earlier also, when the negative of the carrier wave is being applied, then the portion which is connected to the transformer T1 is negative, and the point which is connected to the transformer T2 will be positive. Therefore, for this case, the diode D1 and D2 will be in the reverse bias. Therefore, through these two diodes, current will not flow when the negative terminal the negative pulse of the carrier wave is being applied. But there are two more diodes present in the circuit, and these diodes are the diode D3 and diode D4. Now concentrate on this point. For the negative cycle of the square wave, this point is negative and the right point is positive. When this point is negative, then as we can see from the figure, this point is connected to the N terminal of diode D4, and the right terminal or this point is positive, and this is connected to the P side of diode D3. Therefore, in this particular case, diode D3 and diode D4 are in the forward bias, or they will be in the conducting position. When these two diodes are in the conducting mode, it means that they are connected in the diagonally. They are connecting the points C and D diagonally, and point A and D are connected diagonally through the diodes. Hence, whatever voltage is present at A will be shown at the point D, and whatever input voltage is present at the point C, it will reflect at the point B. Okay, so we can clearly imagine that the pulse which is present in the input will get reversed at the output, because the point A will be connected to the point D and the point C is connected to the point B. Therefore, whatever voltage is applied, because at the input we are applying the modulating voltage, therefore the modulating voltage which was present will be inverted. And for what duration? For the duration in which the negative cycle of the square wave or the carrier wave was present. For this particular duration, the modulating signal will be inverted. Okay. Similar is the case when again the positive pulse of the square wave is present. Then again, whatever voltage is being applied at the input will be reflected in the output on the same side, and again for the negative cycle this portion will be inverted. Hence, the output of the voltage which we are getting in the output resistor of the ring modulator will be somewhat like this. We have applied the positive half of the modulating signal like this. This is the signal which was being applied, and at the output we are getting the signal somewhat like this. Some parts of the modulating signal are getting inverted, and which part will get inverted, it depends upon the duration of the positive and the negative cycles of the square wave. So we have seen the case for the positive half cycle of the modulating signal. Now we will consider the case with the negative half cycle of the modulating signal. This is the negative half cycle of the modulating signal, and it is being applied along with the carrier wave, which is a square wave. Similar is the case when the positive pulse of the square wave is being applied. Then we know that the diode D1 and diode D2 are in the conducting mode. So the point A and point C are directly connected with each other, and point B and point D are directly connected with each other because the diodes D1 and D2 are in the conducting mode. So we can say that whatever voltage is present at the point A will be reflected at the point C, and the voltage which is present at point B will be directly connected to the point D, or in other words, whatever voltage is present in the secondary of the input transformer, that will be reflected, or that will be directly transferred to the primary of the output transformer. Now let us see what voltage is present in this case. The voltage present in the output in the input transformer is the negative pulse. So it will appear as it is across the output circuit for the duration in which the positive pulse of the square wave is present. For this duration, the positive pulse of the square wave is present, and for this duration, the negative pulse of the modulating signal will be reflected in the output. Since we are dealing with the negative pulse, or the negative cycle of the modulating signal. So for this particular duration in which positive square wave is present, whatever is present in the input will be reflected at the output. Now we will deal with the negative pulse of the square wave. We know that when we are dealing with the negative pulse of the square wave, then whatever voltage is present in the input will be inverted at the output, or the voltage which is present, which is applied at the input, will get inverted at the output. Now we are applying the negative half of the modulating signal. So for the negative half of the square wave, for this duration, the input signal will be inverted, or we can say that it will come to the positive half, or it will flip to the positive portion of the wave. Similarly, when the positive halves of the carrier wave are present, all the voltages, all the portions of the voltage which are present in the input, they will be inverted, and for the negative half, they will come to the positive direction. So in the previous two slides, we have seen that when the positive half of the modulating signal was applied, then the output of the ring modulator was like this. This is the output voltage when the positive half of the modulating signal was being applied, and when the negative half of the modulating signal was applied to the signal, then the second wave, or the second part of the wave, was obtained at the output of the ring modulator. If we combine these two waves, then we can get the entire waveform of the output voltage, which is obtained when the modulating signal as well as the carrier signal are simultaneously applied to the ring modulator or the chopper modulator. If we recall the waveform of DSB-SC, when we were discussing the characteristics of double sideband and suppressed carrier wave, and we had illustrated the time domain representation of DSB-SC, then the waveform was exactly what we are getting at the output of the ring modulator. Therefore, we can say that with the help of a ring modulator or the chopper modulator, we are capable of generating double sideband and suppressed carrier modulated wave. Thank you.